Can you hear me? Great. Let's see. This way, it doesn't matter. All right. First thing I'd like to talk about is the title, to make sure everyone's grounded. MESG is Maximum Experimental Safe Gap. And what you see in front of you is the IEC version of the test apparatus on the left side. What we have is some concentric, we have a central chamber, and then around that concentrically is a much larger chamber, and you can see the dimensions. There's a 20 centimeter, a cubic centimeter inner chamber and a 2.5 liter outer chamber. Very large volume ratio. This device measures the spacing needed to prevent a flame from transitioning from the central area, from here, to this external area. It's very similar in concepts to an electrical enclosure. If you're talking about the United States, you would be talking about an explosion-proof enclosure. If you're talking about Europe, you're talking about a flame-proof enclosure. The main principle there is that there is a path length that is maintained very close. This is in a square flange, and this is a circular device where it's threaded. But there's a flame path length that's maintained very tight. By the strength of the system, or if you're thinking about the US box, the more bolts you put into it, the stiffer that flange is. So the idea here is that under an internal explosion ignited by an arcing switch inside this box, that explosion is contained. It doesn't transmit to the outer chamber. Now this device, this particular device, the European device, is very suited for doing this type of analysis with an electrical enclosure. There's another device called a Westerberg device, which has a much smaller volume ratio. The outer volume is a lot smaller in ratio to the inner volume, which then causes some pressure increase in the outer volume, and therefore you get some different results. That type of device, as has been pointed out by Larry Britton, who's in the back, is actually much better when you're trying to evaluate what might happen in a detonation arrestor. It's not perfect, but it's closer, because it does account for the back pressure that could build up. So in this device, we have a viewing chamber. You can see the flame. We have a thermocouple. You can detect the flame. What happens is the material is flown through the devices, through the two chambers in series. The concentration is made homogeneous. The valves are closed. You get a spark ignition, and it either goes or it doesn't go. Now this testing method is very laborious, because it's really two variables. You have the fuel, if you're dealing with a fuel, you have the fuel concentration in air, and you also have the spacing. So you're varying the fuel concentration, and at every one of those fuel concentrations, you're adjusting the spacing till you get to that point where the flame does not transmit. And you can see how this falls generally for materials. There's a minimum that will occur at some concentration. Okay. This concentration is related to the stoichiometric concentration. It's not exactly the stoichiometric concentration because there is a difference in the diffusivity. One of the main reasons that is expected for this difference is that there's a difference in the diffusivities between oxygen and the fuel. So the presumption is that in the fuel kernel, as it's burning, it's actually at stoichiometric, but the concentration in the larger volume is generally slightly rich. There are some where it's not. But in general, you can see there's a lot of test work to determine this variable. So if you're trying to find that variable for a mixture of materials, NFPA says test. That's going to be rather expensive. If you can find a way to estimate this within some range of materials, that would be advantageous. Now, there are a couple pretty well-known methods to do this. One has been published by NFPA. It's been updated in 2008. This method is essentially a molar average, often called Le Chatelier. I can't say that word. Le Chatelier. I'm not French. That principle. Essentially, it's a parallel resistance type of circuit equation. Now, this has been proposed for a while, and in 2008, some of the variables in it were changed, which we'll get to with regard to nitrogen. The other method that is well recognized is the Brandis-Redeker method. Now this method is also a molar average, but instead of averaging the MESG of the fuels, What you're averaging is their fraction of the oxygen used in burning that fuel. In order to calculate this fractional oxygen, you're looking at the molar ratio of the stoichiometric ratios. Now let's do a comparison of these two values, these two methodologies. This is for methane and dioxane. Dioxane is on the x-axis, mole fraction is 1 to the right. And you can see that the NFPA method is a very nice uniform curve between the two values, going from the higher MESG to the lower MESG. In the pink and the yellow, we have experimental data run by Brandes Redeker, and also their curve. Just the molar ratio of the relative amounts of oxygen used for this combustion. In this case, you can see that NFPA is non-conservative. The MESG that is calculated is higher than the actual value, which could lead you into some problems because you'll be potentially using the wrong type of enclosure. Now if we go to a different mixture, this is hydrogen and isopropanol, an opposite shaped curve. Now why is this the case? The NFPA curve is the same shape. Because what we're doing is we're plotting this on the x-axis. We're plotting the mole fraction of the material with the lower MESG value. So the curves are always going to drop left to right. The difference is when you add in the amount of oxygen required, the curve is going to hang with that material that has the higher stoichiometric ratio. So in the previous slide, the higher stoichiometric ratio was with the dioxane. So the curve immediately dropped, approaching the MESG of dioxane. In this case, the higher stoichiometric ratio is with the isopropanol, so it hangs above the curve. Prior to NFPA 497 publishing their MESG method, if you had more than 30% hydrogen in a mixture, it was a group B. When NFPA put out that methodology that we just looked at, there was a way to calculate it. And if you look at this curve, you would see that NFPA is saying, well, about 50% hydrogen can be handled in this mixture, and you're still a group C. That's a great improvement. However, the real data shows that almost 90% hydrogen could be handled in this mixture and still be a group C device. That's a major economic impact. It's very expensive to buy group B enclosures, group C or not. So this can be used to your advantage. So we've shown that the Brandes Redeker method is actually much better at predicting the MESG of pure fuel mixtures. Now we're going to switch gears. We're going to look at some Lund data, and we're going to begin to talk about nitrogen dilution. This Lund data from 1984 was published with some numbers by Geraint Thomas. What he was doing was attempting to look at the flame speed of materials that had the same MESG but were different fuels. So by using the Lund data, he could create a pseudo mixture of any MESG using nitrogen to dilute it. Now what Lund did was he used fuel plus stoichiometric oxygen, and to that he added nitrogen. So with this curve you can see that we have methane in the top section here, and we have ethylene, propane, and hydrogen all coming together in MESG. Very unusual. Thomas actually took the data from about 45% added nitrogen, and that's the data that he published. Now this is a plot of that same data, and you can see very clearly how these materials come together in MESG around about 80% nitrogen. And methane is standing off here by itself. But it's a similar shaped curve. Now taking this data, recognizing that what was tested was the fuel plus stoichiometric oxygen plus some nitrogen. This is different than a standard MESG test. In standard MESG, you have the fuel plus air. So in order to be able to convert this to what was the fuel mixture, we have to take out air. We have to take out the stoichiometric air. So in order to do that, I think it's best to start in the top right of this chart. The original data that was published said that the fuel plus oxygen, fuel plus stoichiometric oxygen was 20%, and to that was added 80% nitrogen. So if we take 1 mole of hydrogen, stoichiometric ratio of 1/2, that means the moles of feed plus oxygen is 1.5. So 4 times that is 6 moles of total nitrogen. So the mixture that we tested was 6 moles of nitrogen, 1 mole of hydrogen, and 1/2 mole of oxygen. We then take out the air. So if all of that oxygen came in with air, we have 1.9 moles of nitrogen that came with that oxygen in the air. Subtract the 1.88 moles or 1.9 moles from the 6, and we end up with a feed that was hydrogen 1 mole, nitrogen 4.1 moles. No oxygen. So that nitrogen-diluted fuel mixture was then mixed with air, and an MESG value occurs. Again, remembering we're using stoichiometric and we're forgetting the diffusivity correction. If you go down further in the bottom line and run the same across, what you find out is that there wasn't enough oxygen in the air. In other words, the nitrogen component limits, which means that this was an oxygen-enriched fuel mixture, not nitrogen-diluted. Now, if we continue with that across all the mixtures, we'll get similar values. What we have done then is taken the fuel mixture moles, back up. Taken the fuel mixture in moles, again, this is the nitrogen-diluted fuel mixture, and we've converted it into feed mole fractions. That's been done consistently. Now, to compare to NFPA 497, that methodology only works for nitrogen-diluted fuels. So let's look at what this tells us for nitrogen-diluted fuels. Again, this is the NFPA equation up here. In 2008, the nitrogen value for MESG, a pseudo value, was set to 2 millimeters. Now, if you think back to what we talked about mixing fuels, what happens when you have a pure you have 2 fuels to mix? The MESG goes between those 2 values in some sort of curve. By setting a pseudo MESG of 2 millimeters, nitrogen is a fuel. So these curves all extrapolate to right there. Okay? Those curves all extrapolate to right there. That's really what's happening. Now, this has some flaws. First of all, there are materials that have an MESG that's larger than 3 millimeters. Ammonia is one. Vanillidine chloride is another one. I think 1,2-dichloroethylene also have MESGs greater than 2. They're in the 3, 3.5, 3.8, something like that. And what you also notice here is that the hydrogen is pretty well matched up to about 40% of fuel. In other words, diluting it down to the point that it's only 40% hydrogen. But look at the other curves. They have the same general shape because they're all converging on 2. But here, for propane, this is the pure fuel. Here is the diluted fuel value. The curves don't represent the data at all. The other thing is that they show no tendency to go through this strange point where everything converged. There is another way, though. We need to try to use the Brandis-Redeker method. See if we can do that. Now, this includes a molar balance on the amount of oxygen, which would imply some sort of a stoichiometric ratio for nitrogen. That doesn't make sense. There's really no way to come up with that. So it's really not amenable to that kind of a pseudo value. But there is another approach. This is the fuel ratio method. And right here, you notice that they come very close to matching the data. I think this is a very important part. The other thing is we're matching hydrogen. We've got the curve shape for the ethylene. Notice how propane is much flatter than the other curves. And up here you have methane. It's not perfect, but It's matching the shapes of the curve very well. So what is this fuel ratio? The fuel ratio is a ratio of the moles of fuel that you would have if you were burning the fuel plus air, dividing that by the moles that you have if you have the fuel mixture that already has some nitrogen in it or already has some oxygen in it, and then you make up the difference with air. So in the denominator, you have what you originally had for fuel plus air, and then you're either subtracting the oxygen that is in the fuel mix, or you're adding the nitrogen that's in the fuel mix. So if you have the same combustion occurring, what's going to happen is that you're going to have the same amount of energy. There's a heat of oxidation that's put into each molecule as it burns. So you have the same amount of energy that's occurring. It's being used to heat up more moles. So it's not going to get as hot, which means when it's on the inside of the gap that we talked about in the testing device, it's already cooled down some. Now, there are a lot of explanations for why MESG values are what they are, so I'm not going to pretend that I know why this is reducing the MESG value this way, but it does work. There are some limitations on it. One of them is that the original data only went to stoichiometric oxygen. So if you're trying to put more oxygen into it than that, you're going to have a problem. The equation, if you look at the bottom of the equation here, it's going to go negative. So that's one reason. The second thing is we now have a way to use Brandis-Redeker because we have a stoichiometric ratio that we're using to provide the amount of oxygen. That stoichiometric ratio can be determined by a molar average of the actual fuel components. Now, what do we do with fuel ratio? Fuel ratio is not attempting to predict MESG of a pure fuel in any way. Instead, what we're doing is we're ratioing the MESG of the pure fuel to what it would be if it were diluted or enriched with oxygen. What's very interesting about this is there is an exponent right here. That exponent occurs from regressing all of the data. So there's in fact a superposition of all four curves. Instead of having three curves almost on top of one another and then methane hanging out by itself, we have all four of these fuels, vastly different burning principles, different diffusivities, all converging. And here you can see the overall curve running from around about a half fuel ratio and actual data out to about 2 1/4 fuel ratio. So by plotting the x-axis as the ratio of the the y-axis as the ratio of the MESGs, and the x-axis as a fuel ratio, we have a single superposition of 4 sets of data for MESG of 4 different diluted fuels. Now this is not, as I said, this is not perfect. Obviously there are things that are missing. Diffusivity correction is missing. If we wanted to dilute with a different fuel, the heat capacity of that different fuel is missing. There are a lot of simplifications that have been taken. However, there's a balance that we have to meet between what's practical and what's perfect, I think, in this situation. Because if we make the gathering of the data to do this so extensive, to make this comparison, we're going to defeat the purpose. And we're going to cost ourselves just as much time and money. But I believe this approach is very applicable, and it also can be implemented very simply in a spreadsheet, as you see here. This is the NFPA example from 497. These are the materials. Spreadsheet can be set up for more fuels. That's not a problem. Stoichiometric oxygen, what the mole fraction is. We have the total for the fuel section, pure fuel MESG values, and then you get mole fractions. Next you have the calculation to end up with the overall average. This is the denominator to make the average of the stoichiometric fuel. And then we have the amount of oxygen for each material. And you can see that we have an undiluted value, comes out at 0.81 millimeters. Fuel ratio is about 0.99. And for the mixture we get 0.83. So again, this is a very simplified methodology, and I'm sure that there are a lot of theoreticians that can explain why this works, but it's very practical. So in summary, the Brandis-Redeker estimation method is much more appropriate than the current NFPA 497 molar average method for the fuel-only mixtures. We've seen the data for that. This fuel ratio method is more appropriate for fuel-nitrogen mixtures and also for fuel-oxygen mixtures, which is a dramatic improvement over the current situation. If we put the two of these together, I believe we have a very simple and appropriate methodology that we can use to estimate the MESG of fuel mixtures diluted with nitrogen or enriched with oxygen. So I appreciate the time that you've given me to speak with you, and I'd take any questions. Please, Larry.
Larry Britton. Quick question. In that 2002 article I did on heats of oxidation, there was a very strong correlation between heat of oxidation and MESG, including, and it stacked the zone groups up pretty well. Did you look at that, and is that in any way related to the Brandis-Redeker method?
Oh, it's very much related to that. The Brandis-Redeker method is the amount of stoichiometric oxygen needed. Okay. So it's very definitely related to that. This probably could be cast in both ways.
Do you think this is something that could be worked into Cheetah?
I don't understand why it couldn't. I believe absolutely it could. Because the methodology of calculating what the actual resultant flame temperature would be is perfect.
Okay, so that's another job just for Cheetah. What's your opinion on using MESGs as substitutes for hazard class inflammability, which is being done in Europe? I don't like it myself.
There needs to be some limit on maximum MESG where it's not appropriate, in my opinion, to require electrically classified equipment.
This is being done, like, for example, in the IEC static electricity document, which is being worked on at the moment. They look at different ignition types, and instead of relating to ignition energy, that they relate it to the the zone group. Have you come across that? It doesn't make sense to me, but the reason they do it is because they can look up the zone. They can look up the zone group much more easily than they can the MIE.
Oh, well, they're trying to simplify things.
That's right.
There is an advantage to simplifications, but I think sometimes it can go too far.
Is there, in your article, a derivation of the Brandis-Redeker method, or is it kind of empirical?
It's not in my article. There is a Brandis-Redeker paper that's referenced in my paper. And in that paper, there's some discussion, but it's not theoretically derived. It's
Okay.
empirical.
Thank you.
Doug Hisson with ExxonMobil Upstream Research. I'm wondering if there's a connection between predicting MESG and predicting lower and upper flammability limits, because that Le Chatelier blending reciprocals is a simple way of doing flammability limits too. So I'm wondering if there's something analogous to Brandis-Redeker that you can use for flammability limits.
I think you should speak with Larry.
Yeah.
His paper includes all of those things, and there are correlations that do exist. There's an advantage in being able to predict things from first principles. This is not trying to do that. This methodology is only trying to start with a test value and then extrapolate that to mixtures, which I believe is where many of us in industry have a concern that our mixtures vary, and we don't necessarily want to spend all that money for testing each and every mixture, so we'd like to have a methodology. I should point out that whether you're talking about the NFPA 497 method as it currently stands or the Brandis-Redeker method, they all have issues with carbon monoxide. They both have issues with carbon monoxide. There are issues with some sulfur compounds as well. So there are limitations in application, and if you want to do this, I'd encourage you to read the underlying papers. Any more questions?
Vince Van Brunt, University of South Carolina. Yeah, as you get to fuel-rich mixtures, you start getting a fair amount of CO. And just what your comment was on CO. Have you done anything particularly looking at where you start getting a lot of CO present?
No, I have not. This methodology is for helping to establish what the proper electrical classification is. What you're talking about is something in an operating system, a burning system. Instead, what we're talking about here is a fuel mixture inside a device, and you're trying to ignite something outside the device. So obviously you're going to be diluting, you're not controlling the concentration, so to get a fuel-rich mixture in a large area like that is not as likely. All right, if there are no more questions, I thank you for your time.